Hello everyone, welcome to lecture 9. The plan for this lecture is as follows. In this lecture we will consider the notion of stream cipher, where we will see how to encrypt long messages using short keys with the help of pseudo random generators, and we will also see the restrictions imposed by stream ciphers. Namely, we will see that stream ciphers does not support key reusability. For this we will also introduce the notion of multi-message security. So, on a very high level, stream cipher you can imagine as if it is a pseudo one time pad. So, just quickly recall the one time pad scheme, where the message space, key space and ciphertext space all consist of bit strings of length big L bits. The key generation algorithm outputs a uniformly random key of size L bits, and to encrypt a message of size L bits you simply perform the XOR of the message with the uniformly random key, and the decryption operation is just the XOR of the ciphertext with the key. Now, in the stream cipher, the key space is going to be set of all possible strings of length little l, where little l is going to be much smaller than the big L. So, we have now two different spaces here. The key space is different and the message space and the ciphertext space are different. The message space and the ciphertext space consist of all strings of length big L bits, where big L is significantly larger than little l. So, the first change that we are going to make in the stream cipher compared to the OTP is that the key generation algorithm is now going to output a key which will be of size little l bits instead of big L bits. And to perform the encryption operation, we will actually XOR the message with the output of a PRG invoked on the key generated by the key generation algorithm. So, in the stream cipher we assume that we also have a secure PRG extending or stretching little l bits to an output of big L bits. So, by running the pseudo random generator on the seed k on the key k, we generate the mask, and that mask is XORed with the message, and that produces the ciphertext. The same operation we perform at the decryption end. So, in stream cipher we have different nomenclature followed in the literature. We have few sources which says that the entire encryption process is called a stream cipher, whereas we have other sources which says that the instantiation of the pseudo random generator is called a stream cipher. Now, irrespective of whether we are following definition 1 or definition 2, the important thing is that the message M is actually XORed with the outcome of the pseudo random generator on a uniformly random seed, which is of much smaller size compared to the message size. Now, the reason that this whole encryption process or this whole system is called a stream cipher is that the bits of the plain text, all the bits of the plain text need not be known in advance. That means, for moment imagine that your capital L is say 1000, right. That means, you want to design an encryption process which can encrypt messages of length 1000 bits. And for instance, imagine that you have got a message, you have obtained only say the first 100 bits of your message, right. So, since you have only the first 100 bits of the message, what you can generate it, you can actually run the algorithm G and produces the first 100 output bits of your algorithm G on the input K, and that actually constitutes the stream with which you can actually XOR the first 100 bits of the message and send it to the receiving end. Next, if you receive the next few bits of the message, you can produce the next few output bits of the algorithm G on the same input K to produce the next sequence of pads with which you can XOR the next sequence of bits of the message and so on. So, you can imagine that actually your algorithm G is producing the sequence or a stream of pads depending upon the sequence of bits of the message which are available to you, and that is why it is called as stream cipher. The whole message need not be available to you in advance. So, now let us analyze that why this stream cipher is secure. So, the claim that we want to make here is that if your algorithm G is a secure PRG, then the stream cipher that we have designed is semantically secure. That means, it is computationally indistinguishable in the ciphertext only attack model. And the proof intuition for proving this claim is as follows. What exactly is the difference between the one time pad encryption scheme and the encryption scheme that we are following in stream cipher? Well, the only difference is, in the stream cipher, the pad or the pad with which we are actually masking the message is actually pseudo random, whereas the pad which is used in one time pad is truly random. That is the only difference between the two encryption process. That means, we have already proved that in the context of one time pad, no distinguisher can distinguish apart whether the ciphertext C is an encryption of M0 or M1 except with probability 1 by 2. We expect almost the same to hold even for the stream cipher. That means, no polynomial time distinguisher should be able to distinguish apart whether it is seeing an encryption of M0 or whether it is seeing an encryption of M1, because if we have a distinguisher who can distinguish apart an encryption of M0 from an encryption of M1 with a significant probability better than half, that means that adversary knows how to distinguish G of k from a uniformly random k, which is again a contradiction to the claim we are making about the security of the algorithm G. So, we formally establish this intuition through a reduction based proof. So, we are given the publicly known pseudo random generator and we consider two encryption process, one the stream cipher and the second encryption process is the one time pad process. Assume for the moment you have an algorithm A, right, who can actually win the indistinguishability game in the ciphertext only attack model against your stream cipher. That means, we are making an assumption that our stream cipher is not semantically secure. By that we mean we have an adversary A who can win the ciphertext only attack model indistinguishability game with probability half plus non negligible. Using the help of the algorithm A, we want to design another algorithm D who can distinguish apart a pseudo random sample produced by G from a truly random sample, which will contradict the claim that we are making about the algorithm G, right. So, the algorithm D participates in an instance of the indistinguishability based game for the PRGG, where it is given a sample y of size big L bits and it has to find out whether y is generated uniformly randomly or whether the sample y is generated by running the algorithm G. Now, what D does is it actually participates in an instance of the COA indistinguishability game against the adversary A. So, my distinguisher D is now playing a dual role here. On the left hand side part of the experiment of the reduction, it is actually participating as the distinguisher and trying to distinguish apart whether y is pseudo random or truly random. Whereas, in the right hand side part of my reduction, D is actually participating as a verifier of the COA indistinguishability based experiment. So, as part of the COA based indistinguishability based experiment, the adversary A throws a pair of plain text messages M0 or M1 as per the choice of the adversary, and the distinguisher D has to randomly encrypt one of these two messages, either M0 or M1. So, it decides the index of the message, which I denote by capital B, and with probability 1 by 2 it could be either 0 or 1. Now, to encrypt the message M of B, it has to actually select a pad, right. So, what the distinguisher D does, it uses the sample y which is given as a challenge for the distinguisher as the pad, and it masks the message MB with the challenge y and produces the ciphertext C and gives it to the adversary A. So, now if you see what exactly is happening here is, if the challenge sample y which is given to the distinguisher D is uniformly random, then what the distinguisher D has created here for the adversary is an instance of the OTP based indistinguishability experiment, because in that case the challenge ciphertext would be an encryption of the message MB as per an instance of one time pad, because y would be truly random. On the other hand, if the challenge sample y is pseudo random, in that case D basically has created an instance of indistinguishability COA based indistinguishability experiment as per the stream cipher, because in that case the challenge ciphertext C would look like a challenge ciphertext which adversary would have seen by participating in an instance of COA indistinguishability experiment against the stream cipher, right. Notice that the distinguisher D does not know whether it has created an instance of OTP experiment or whether it has created an instance of stream cipher experiment, right. Now, depending upon what type of ciphertext C is given to the adversary, adversary A gives an output. That means, it tells whether the ciphertext C is an encryption of message M0 or whether it is an encryption of M1. Now, using the response of adversary A, D has to find out what exactly is the type of y, whether it is truly random or whether it is pseudo random. So, here is the decision output of my algorithm D. If it sees that the adversary A has correctly identified what is encrypted in C, that means the index B double dash is equal to the index big B, then the distinguisher D labels the sample Y as if it is generated by a pseudo random generator. Otherwise, it labels the sample Y as if it is generated by a truly random generator. That is what is the idea of this distinguisher. Now, let us calculate the distinguishing advantage of the distinguisher. Let us first calculate what is the probability that the distinguisher D we have constructed labels a truly random sample Y as an outcome of a pseudo random sample. Well, this is exactly the same probability with which an adversary A participating in the COA indistinguishability experiment against one time pad would have won the experiment, because if b little b is equal to 0, that means the sample Y is truly random, then the challenge ciphertext C which is given to the adversary is as per an instance of OTP, and with whatever probability the adversary A would have won the indistinguishability game against OTP, only in that case the distinguisher D would have output B dash equal to 1, because remember the strategy of D outputting B dash equal to 1 is if my adversary A can win the indistinguishability game. So, if A can win the indistinguishability game against an instance of OTP, then D would have labeled a truly random sample as a pseudo random sample, right. On the other hand, and we know that the probability with which the A could win the COA indistinguishability game against an instance of OTP is half. On the other hand, the probability that D outputs B dash equal to 1 given that B is equal to 1 is exactly the same with which my adversary A can win the COA indistinguishability game against an instance of stream cipher, and as per my assumption it is 1 by 2 plus some non negligible probability, right. So, overall the distinguishing advantage of my distinguisher that we have constructed is the distinguishing advantage or the difference in the absolute probability with which the adversary A could win the indistinguishability COA indistinguishability game against an instance of OTP and against an instance of stream cipher. And if we take the absolute difference of these two probabilities, it turns out to be epsilon. So, if I assume my epsilon to be non negligible probability, then it implies that I have constructed a distinguisher D who can distinguish apart a truly random sample from a pseudo random sample with the same probability, and that will contradict my assumption that algorithm G is a secure PRG. So, even though we have now solved one of the problems or the limitations of perfect secrecy, namely we have seen a mechanism namely Ciphers where we could encrypt arbitrarily long messages using short keys, it turns out that we cannot get rid of the second restriction. That means we cannot encrypt multiple messages using the same key with the help of stream cipher. So, for this recall the single message semantic security. So, in the single message semantic security the goal was that sender encrypted a single message using a short key, and by eavesdropping the ciphertext we wanted to ensure that adversary could not compute any function of the underlying plain text. Whereas, for the multi-message semantic security the requirement is that now sender would like to encrypt a sequence of messages using the same key, and those ciphertext are eavesdropped by the adversary, and we want to capture the intuition that seeing the ciphertext does not help the adversary to compute any function of the underlying plain text with a significant probability. And we can model this requirement as an indistinguishability game. So, in this indistinguishability game which we call as prive k COA mult, because we want to capture the multi-message security experiment, the rules of the games are almost identical as it was in the single message indistinguishability game. The difference now is instead of sending a pair of messages to the verifier, the adversary will now submit a pair of vector of messages of polynomial size. And this basically captures the scenario that the adversary would like to distinguish apart whether sender has encrypted one vector of message or the other vector of message, right. So, there is no restriction on what type of messages adversary can put in these two vectors. The only restrictions is that the overall size of the vectors is should be a polynomial function of your security parameter, and if we consider the first message in the 0th vector and the first message in the first vector, they should be of same length, and the same holds for the ith message in the 0th vector and the ith message in the first vector, and so on. Now, what the verifier is going to do is it will run the key generation algorithm out and obtain a uniformly random key, and with the help of the key it is going to encrypt all the messages in one of the vectors. That means, it will randomly choose one of the vectors with probability 1/2, it could be either the 0th vector or the first vector, and it is going to encrypt all the messages in that vector. And the challenge for the attacker is to find out by seeing the ciphertext which vector has been encrypted, whether it is messages in the 0th vector or whether it is messages in the first vector. And the definition of our multi-message security is, we will say that our encryption process is multi-message secure in the COA attack model if for any polynomial time adversary participating in this experiment there exists a negligible function such that the probability with which our adversary A could output B equal to B dash, that means it can correctly identify which vector has been encrypted, is upper bounded by some half plus negligible probability function in the security parameter. Again, why 1/2? Because there is always a guessing adversary who can just guess which vector has been encrypted, and the extra negligible function here is to model the fact that we are in the computationally secure world. So, we are willing to give the adversary a negligible extra additional negligible chance that it can break our scheme, right. An alternate security definition for the multi-message security in the COA attack model is that the distinguishing advantage of any polynomial time algorithm participating in this experiment should be upper bounded by a negligible function. That means, irrespective of whether it was the 0th vector which is encrypted or whether it is the first vector which is encrypted in the challenge ciphertext C, the response of the adversary A should be almost the same except with some negligible probability. So, either we can use this definition or we can use this definition. It turns out that both these conditions are equivalent to each other. So, now let us quickly see that why stream cipher is not multi-message secure, right. So, here you are given a stream cipher, and the main reason that your stream cipher is not multi-message secure is that the encryption process in the stream cipher is a deterministic algorithm, right. That means, if you encrypt the same message M using the same key multiple times, you are going to get the same ciphertext C, and that is basically a loophole which any adversary could exploit in the multi-message security experiment, right. So, what I am going to show you is an instance of an experiment where any adversary can break the notion of multi-message security against your stream cipher. So, what the adversary is going to do is it is going to submit a pair of vectors, where in the 0th vector it has actually submitted two messages, both consisting of strings of length all zeros, and in the second vector he has actually it has submitted two messages where the first message is all zeros and the second message is all ones, right. And as per the rules of the experiment, the verifier is going to randomly encrypt the messages in one of these two vectors by using a key generated by the key generation algorithm. And once the adversary sees the challenge ciphertext, it is very simple for the adversary to pinpoint whether it is seeing the encryptions of the message in the 0th vector or whether it is seeing the messages in the first vector. Basically, his strategy will be to just compare the first ciphertext with the second ciphertext, and if they are same, then it implies that he has actually seen the encryption of the message in the 0th vector, otherwise it has seen the messages in the first vector. And this basically actually coming from the fact that your stream cipher is deterministic. So, an encryption of the message all zeros is always going to produce the same ciphertext if it is encrypted multiple times with the same key, right. So, that brings me to the end of this lecture. So, in this lecture what we have seen is, we have seen that using the help of pseudo random generator we can actually encrypt arbitrary long messages using short keys, and this is done to the help of stream ciphers. However, stream cipher does not gives us the security against multiple messages. That means, it does not allow you to reuse the same key multiple times, right. So, I hope you enjoy this lecture. Thank you.